about what information we already have towards modeling laminates and packages, talk about some of the challenges with modeling the metals, the dielectrics, and this is very open-ended in terms of trying to discuss what test structures might be there, show you some real-life complications. Some of these may not be really measurement-related, but simulation-related, things like fill patterns and stuff like that, and then talk about some of the on-wafer challenges and then summarize. So why do we care about characterizing laminates? Well, basically, every single module we build, this is the backbone for the module. And the thing that makes PAs different about a lot of the other circuits that people would use is that this is actually part of the circuit design. So the matching and things like that in the laminate are actually part of the circuit design. And you can also see here that they're relatively complicated, 9, 10 layers. We'll talk more about what these shapes look like later. But the other thing to keep in mind is that these things are usually about 9 by 9 millimeters when you look at this guy, which is a little bit different than a normal PC board where you can have this is not millimeters, it's inches. So accurate laminate parameters are required for simulation development. So if you put garbage into the simulator, you're going to get garbage out. The main driver for this is saving time and money to get your design right and not have it be chasing the tails of whatever the laminate happens to be doing that day. I'll talk more about what we have in terms of physical database. The other thing is, besides modeling, having an accurate way to look at the electrical parameters of the whole laminate together, the dielectric and the metal, allows us to make unbiased, data-driven decisions on laminate technology improvements. Designers tend to get distracted by shiny objects, so this just kind of removes that out of the equation. There's some similar things on wafer that you got to worry about, and I'll talk about those later. And the other part of it is, as we move towards 5G, there's probably going to be ways to drive decisions between whether you put your match on the laminate, an integrated passive device, or on and what SMDs you use, and whether you put it on, how much of it you put on the laminate or in the laminate. Right? So we've got a bunch of stuff. So what's the problem, right? We get a lot of physical data, which I'll talk about. It doesn't tell the whole story. And this is mostly what you get from the vendors, is the physical data. The suppliers focus on the fundamental material, not on how we use it. I think there was a talk yesterday that talked about dielectric characterization. That's awesome, but the problem is we've got interactions with the way the things are built, right? So you've got these dielectrics and the metals, and there's a lot of interaction between the two things, so you can't really characterize them separately. And we don't have something like process control monitors. And this interaction is a little bit different. Like, say for a semiconductor, we buy a wafer, we process the wafer, the vendor can process it too, we can compare our data, and we give them process control monitor feedback to tell them whether the wafers were any good or not for what we're doing. We don't have a way to do this feedback path for laminates. Okay, so that's a critical problem. These interactions I'll talk about. So there's also a lot of variation, and that means like doing one measurement on one laminate does not help you, right? You've got to know what the statistics are and keep driving that. And you need it to be sort of across like real designs helps too. For cell phones, we're in a situation where we, just use a better material. Well, we can't. Phones already cost $1,000. Nobody wants to pay more than that, right? So if we have to use better material, it's going to drive the cost up. And in turn, if we're using better material, the foam board it's going on is also going to be more expensive too. So it's just going to drive cost up. Typically, the vendor data, and I'll go into this in more detail later, is usually single points. The designs are wideband, so it's not so great to have single points. And there's not a lot of high-frequency data available on sort of the typical available laminates that we have right now, and I'll show some things on that in a little bit. And so the on-laminate component validation is left to the customer, which is whoever happens to be buying the stuff, which is kind of why I'm here talking about this. So some of the things that go into laminates, there's transmission lines, solenoid inductors, so inductors where, in this case, you can see these guys where they're wrapped around and they go down multiple layers. Those things, they matter a lot. And then there's also the unintentional coupling of capacitors, and then there's vias. And these are all on multiple layers. So and the layers aren't such that, you know, the top metal doesn't have another thing on top of it, so you've got to characterize that separately than one that's like, you know, sandwiched in between. So they are a little bit different in that case. So what would be great, right? So the thing that would be really awesome is if we had a set of standards like, oh, I don't know, the on-wafer calibration structures that Marco and Andre talk about, having something like that on a laminate would be fantastic. Process control monitor structures, they've got their own set of requirements. They can't be destructive. They should be simple to test. If if it requires a large amount of fitting or complex routines, the packaging guys are just gonna just cry. It won't work. So you can't do it that way. There's been some people that have used on-laminate resonators, but when you look at what they're doing, a lot of times you're not extracting the parameters individually. You're getting a resonance frequency and things like that, but you're not getting information about the metal and the dielectric independently. You can get the dielectric stuff, I think. So what would be great is like a few transmission lines, maybe some 4-point probe structures for DC, just to monitor and control. And they've got to be small enough to not require that you use like an entire strip of the laminate. And I'll show a strip later. And it's better if the structures that we use are as close to the final application as possible. So for those of you who have not seen laminates, basically, you've got these dielectric layers, you've got metal traces, you've got vias going between them. Call your attention to the thicknesses and the tolerances here. So if you look at the metal thickness is like 14 microns. And you look over at this column, you see like, oh, plus or minus 5, is that percent? No, that's actual values. So this is like varying by plus or minus 50%. Okay, so that makes it really challenging. You have to know that. So if you see people just characterize one thing and then they fit it, it may not even be close to reality because they're assuming that they got the thickness that they ordered, and it can be off by a lot. And then the other thing to call your attention to is there's very little information on the dielectric constant and the loss tangent. It's not at very many frequencies and only up to 10 for what we've got to date. So that kind of explains kind of what's going on. The other thing besides the thickness variation is that the registration, the alignment between this layer and this layer is really bad. It's like, plus or minus like 15 microns. So I've seen people try to build couplers back in the days when it was plus or minus 25 microns and use a 25 micron line. I don't think that worked. It's like they weren't even on top of each other anymore. So that's the kind of thing that we're talking about here. So what goes into the simulator for the EM stack? Because we want to be able to drive good simulation. I just happen to use momentum as an example because I happen to have it on my laptop and can pull the pictures out really easily. But you've got the vias, you've got the dielectric thickness, metal thickness that go here. And there's another tab where you can put in the material parameters. So there's dielectric constants, loss tangents, and these are mostly frequency independent the way they're implemented right now, which I think is probably not the best thing to have when you're trying to do 5G stuff. But this is what we have right now. And then when you look at the metals, you get conductivity, and the conductivity has also got no dependence on frequency. So the assumption is, and I'll talk about this later, it's a single metal with a given conductivity, right? Which is not ever how anything is built on wafer. And then on the laminate, there's also some other little gotchas. So what information do we get already? So this looks like a lot of data. You get the thicknesses of the metals, thicknesses of the electric constants, and it becomes a big simulation problem to include all this. So some of the stuff you just throw out, which are these kind of guys, are not really related to what you'll get and we have to worry about from a simulation point of view. But the other thing that's kind of nasty is there's not really much correlation between the layers. So maybe the top layer and bottom layer will correlate with each other, and then everything else you're kind of on your own. So it's a big simulation problem. So that's one of the other challenges there. So this is an example of the data that I showed before from the table that we get from different vendors. So we've got material set, and I've removed the vendor names so that people wouldn't freak out about it at work. Different suppliers, different materials they have, and you can see the dielectric constants and the loss tangents that they show. And there's A few people will go higher frequency on stuff, but not everybody. Then there's this other technology, which is, and this is using like a prepreg material, which is like what I showed before. There's another one which is like resin-coated copper, where there's the copper and it's just embedded in resin. That's another option for stuff that people have. And you can see like the loss tangents are a little bit different, but there's no way to know how they measured it or how realistic that is without measuring it yourself. And then there's the solder mask that goes down anywhere you don't want solder to bleed into, that gets put down on the mask. And that's on the top, so you have to worry about that for some cases. So how do they measure it? Well, right now, most of the information that we get from the vendors comes from this like split post dielectric resonator. And I think the NIST guys have published a lot on that kind of stuff. That's the main thing. Strip line probably looks closest to what we will use in real life, but not a lot of data from people on that. So there's a lot of different methods to use it, and then the usual frequency band and sample form are different for these things, right? What we'd like is something where we can actually put it down in the laminate. We don't want to have to do, and I'll show this later, there's different sizes you need for the different frequencies for these, the split post resonator samples and things like that. So it makes it a little bit challenging to try to do something like what we would do on wafer with the laminates. So here's a really fun part of this, which is the challenges for metals. So the metals that we drew all look like really great rectangles, right? That's very disappointing because they don't look like that at all. I'll show pictures. There's surface roughness, which is going to depend on how you, the process you use and how you make your transmission line. Where's the current? Is it on the top or the bottom or the sides? And at higher frequency, the roughness starts to really kill you. And that's kind of where the connection with 5G comes. And also there's a composition problem too, which I mentioned, which is if there's nickel on the sidewalls, it's a killer. I'll show an example of that. And then very thin metals may not be modeled adequately for high frequency. This applies more to on-wafer stuff. So the example that sort of drove looking at some of this originally was, we had a designer call up and say like, oh, we got this stack from somebody and they gave us this conductivity for copper. It doesn't even look like copper. And we're trying to explain like, yeah, well, they probably just kludged it for the surface roughness and some other stuff, and that's why you wound up with it. And that's kind of what drove looking at some of this stuff. So here's some of the fun shapes you can get with the metals. You get undercut. They look rounded. Depending on which process you use, you can get these sort of trapezoidal kind of guys with a weird foot on them, or you can get something that looks closer to a rectangle. But if you're assuming a rectangle and get either of these two guys, like the edges for this look so different, like the edge coupling would be completely different than if you got something like this or something like this. So this is a big challenge for EM, is knowing what do you really have on the wafer when you go to simulate it. You can probably make some assumptions and get things closer, but I've not seen any of the papers where people were doing this that they actually cross-sectioned what they were measuring to go validate that what they simulated was what was really on the wafer. Here's another good one, which is you don't always get what you draw. So vendors compensate these things. You lay them out a certain way. They'll adjust them so that it complies to their design rules. In this case, we got this really cool scalloped feature, which was not what was drawn, okay? And I'll show the impact of that in a second. So the compensation, you can do this, and I've seen things where if somebody was aggressive and tried to draw something below a design rule, the vendor tries to compensate it. They go to make it bigger and compensate it. Well, they have to chop it when it's below their rules. So you drew these two lines together and like half the line is missing because they compensated it to make sure they could build it. And so that's why, another reason, you have to know what's really going on before you try to simulate it, because it could be completely different than what you thought you had. So this is kind of the example where it got so actually the signal trace and then all of these guys traced got simulated versus the original layout. And you can see it can account for like a 10% change in the inductance. Okay, when you add this with the changes to the metal thicknesses, overlaps, because these are like a solenoid kind of thing, it can amount to very, very large change in your inductance that you didn't know you had. And for whatever reason, laminates are always assumed by designers to be perfect, right? And so when you start showing them the variation, it's mind-blowing for them because like, oh my God, I didn't know it could do that. Well, it can. So that's a big problem. The surface treatments, so these are just 3 different surface treatments in an attempt to get the surface roughness down. The CZ doesn't stand for anything particular, it's just the treatment they have. So that one's kind of rough. This brown oxide is another treatment, that's a little bit better. And then you've got the smooth trace that's 0.32, which is better. But here's the problem. As we go up and look at the skin depth in copper for this stuff, right, as you go up to 30 gigahertz, you're starting to get skin depths around the roughness value, right? And that can basically, 60% or even at some point double your loss, right? So if you don't know that you've got that's a big deal. You're gonna have all this loss and like, oh, this is terrible technology, you don't know what's going on, and it's because of this kind of stuff. And so like I said, at higher frequencies like 5G frequencies, this becomes a very big concern, the surface roughness. This is an example of how the nickel on the sidewall can really kill you. At some point in like 2012, 2013, there was a transition from nickel gold plating on top of the copper to protect the copper from oxidizing to nickel palladium gold. And when they did this, they made the gold a lot thinner. So you could see all of a sudden your loss is going up a lot. And this was a simulation showing bare copper, nickel gold on top, and then when you put it on the sidewall, what happens? And that was really the thing. People were looking at it, just stacking it up. Well, having the nickel on the sidewall is a bigger problem. It starts to kill your performance. Like if you look at the power loss, it goes up by almost 0.9, and so that's a big deal. So knowing the details of the metal stack and what you're measuring also matters, because designers were looking at this. Depending on how you did the layout, you could see the impact of the nickel more or less, depending on how you routed your bond wires to it. And so some guys are like, oh, I don't see a problem, and other guys are like, yeah, this is killing me. So you have to know the details of the metal to get this right. And that's not always explicitly known. The dielectrics, this is kind of what I was looking at, what we were looking at before on the other chart. Most of this work for these high frequency boards is really driven by the digital guys, not so much by the RF guys, right? So you see almost all of these papers where people are publishing these kind of things. It's always in the context of digital, not in the context of RF. Like you're not seeing inductors measured, transmission lines measured, any of that kind of stuff. It's always like, line delays and loss and things like that. So the vendors tend to use these kind of measurements. They're getting more towards using, something closer to like transmission lines and like up to higher frequency, like the microstrip lines and things like that. That's probably more what we want, is driving towards that. So this is just an example of what those guys are doing. This is the explanation of the split post resonator, where you've got the cavity. You measure it, I think, with this not in the cavity and with it in the cavity. It gives you the dielectric characteristic in the plane, which is okay. I mean, when you lay things out, it's going to be this or this. This kind of gives you an average, and it works out to be okay for most simulation at least low frequency. I'm not sure at high frequency. But the other thing that you see here is the sample size is different depending on what frequency you're at, right? So this isn't something you could go do and easily place on a laminate and run as an experiment. It's got to be done in this. So it's not something you could use to track what's going on with a particular laminate process. And this is just an example of some of the high-speed material data sheet that we get from people. Different vendors, different materials they have, different dissipation factors. So lower, you want it lower to be better. But here they're only showing up to 10 gigahertz, and this is high speed, right? And for 5G, we're talking about much more than that. So getting characterization up to higher frequencies is something that's kind of critical going forward. And these workability things, the thing I forgot to mention on the roughness part is, if you make the surface really smooth, the next layer on top of it doesn't want to stick to it anymore. right? So it needs to still stick together mechanically, right? Because these things are going to flex and things like that. So that's another important criteria, is like it can't be perfectly smooth or it's not going to stick. So or they've got to do different chemistries to get it to stick better. So here's an example of a strip. So there's a bunch of different potential designs you could plop in here. This one here is actually a couple of transmission lines. So what we'd want to do is to have something where you could take maybe a few of these and convert them over to monitor structures. And from a practical point of view in a company, I'm not sure you'd want to do it necessarily on a production stuff, because then you're just throwing away potential die you could sell. But when you're doing pizza laminates, you could do it and keep track of it. If you're running enough of them, you'll capture what the process is doing. So that's the kind of size that we're talking about. These are all like 9 by 9 little slots. So some of the potential test structures. This is out of, these are the references for this, but the BD came up with this structure where it's basically 2 different line widths there, and you can get the thickness and the width from that sort of structure. But these are all done in like assembled, right? Like in package testing. We didn't find any references where people actually did this on wafer very easily, right? These guys were doing stuff where they were trying to look at very high frequency on laminate, and what they were pointing out in this paper was there's some issues with the pad design. But again, they're trying to model this, but I didn't see any cross sections that show that they actually got what they asked for from the vendor. So that's a little bit. I mean, I think the concept is good, but I don't think that the execution was 100% great. And then there's other ways to look at these things, and these may or may not work very well. But at least these are just some ideas for how maybe we could do a PCM type structure. So to get DW, you can use standard line techniques, and you can get the conductivity if W and T are known. So it helps double check for the RF measurement too if you use DC stuff. So more fun structures. The vias pretty much don't. The vendor never talks about those, right? You don't see what's going on with those at all. There's some on-wafer techniques to do via measurement that Marty Brophy came up with, where you've got a via here, via here. I don't see anything that really prohibits you from applying that on wafer, right? So that, or I'm sorry, on a laminate. So in theory, it should be able to work on there. And this just gives you an idea. Some of the problems with laminates, like you can see these vias are not cylinders at all. And it's not on some of the layers. That's kind of a problem. Copper pillars, which are quite often used for assembly, you can go through, there's no 2 pillars that look alike, right? So, but people always simulate these just saying it's a cylinder, but when you look at it, when you go to match it to the board, solder goes all over the place, right? So that, I would assume, simulates differently than if it doesn't go all over the place. And this is, I'll talk about the on-wafer stuff later, but another really big problem is when you look on wafer and look at these kind of vias, how the fab guys measure the wafer thickness is not necessarily how you think you would. They'll just take a profilometer, flip it over, and measure the thickness. So when they say the wafer thickness, you have to ask them for a cross-section to make sure that you're looking at the gallium arsenide thickness, not the thickness of the gallium arsenide plus whatever stuff is on top. It makes a big difference. Because there's some fabs where, 4 mils is 85 microns because of that. So it's just another thing to keep in mind. So some of the real-life complications with some of these things are like local pattern density. And I don't know if Scott will talk about that when he talks about his silicon stuff, but the local pattern density can be a problem. So if we've got 2 traces where you've got a very wide line and then a thin line surrounded by 2 wide lines or just on one side, you get different trace thicknesses for that, right? So if we're going to build calibration structures, we have to keep that in mind, that you can't compare something like this and this because they're going to physically be different. The way these things etches is different too. So some narrower trace etches faster than the thicker trace and things like that. So when we're talking about trying to build like a TLM type thing or different transmission lines, you have to take into account that there's going to be some bias just from the etching. And then with clearances, you have to worry about it too. If you don't have enough clearance, these etch differently too. So when you look at the spacing back to the ground, it can be very different. All right. So another fun one is at the metal percent, and this is where some of the interaction starts to come into place. If you look at pizza panels and pizza strips, the dielectric thickness changes with the metal pattern density, right? And so if you've got this percent of remaining metal, you've got different amounts of resin that are left, so different amount of dielectric that's in there, and it's got a different composition, right? So you've got this thing where the dielectric constant can be changing depending on the pattern density of the metal, right? This is more, if it's characterized, it's more of a TCAD issue or a PDK issue to put it in, but it's something that can happen that people don't normally consider. So a lot of the transmission lines, they're very sparse, right? So there's not a lot around them. There's other things where people try to fix the metal percentage by putting fill patterns in, but they're running a transmission line over one fill pattern, and then the next transmission line over, there's no fill underneath it. So you're not really characterizing what you think you are when you're doing that, because they're just like different metal blocks underneath. So that's a problem. And a dummy fill is needed because on opposing layers, if the percentages are different, it'll warp, right? So that makes it hard to put the pieces down on it. That's one of the problems that we've got with that. The trace width and copper thickness stuff we talked about a little bit. And the whole thing here was, sort of driving the designers when they're putting different designs on a laminate to try to group them by pattern density or fill them so that they kind of look the same and they're not comparing apples and oranges off of the same strip even. So that's the other thing. So 1 micron thickness increase for each 10% increase in remaining metal. The other problem is that from a PDK, in silicon you would normally just look at your pattern density on your die and do that simulation, say, okay, I got my fill, I'm done. I'm good, I know what everything looks like. The problem here is as you go through the different stages, so the module, which is like the little tiny 9x9 guy, up to a strip, which is what I showed before, and in the panel, which is a couple of strips, the metal percent density changes, and it can change enough that you're changing it by like a micron and a half on the metal, just because of that. So that could be a problem. So the issue is there, once you've got a module that works, then you want to go to a single variant, right? You have to make sure you didn't jump into a different bucket on that percent metal fill. Otherwise, a lot of things change and you're like, oh, well, it works great on the pizza laminate. Why doesn't it work in the production laminate? It's like, well, because you may have kicked over into the next bin and changed a lot of stuff that you didn't intend on. So there's that, and then across the strip, because of the local pattern densities, you can have thicker metal in the center and things like that. So when people are like, oh, well, I only measured one, it's like, well, you should probably measure some of them in the areas you think they're going to be different in, because we would try to ship stuff from here. So you better test all of the possible places where there's the metal thickness. Don't assume it's perfectly uniform. This is the dummy fill to control the warping stuff. And so this was one design versus another design, versus another layer. And then this is the layer with the dummy fill added so that it can balance out with this layer 8 here. So these guys you want within 20% of each other. This is really more of a PDK thing where you want to do the fill, but the fill needs to be smart. So like I was saying before, don't put the fill underneath lines, don't put it sort of between lines where they can couple. There's some intelligence that has to happen. You can't just start dropping blocks of metal down everywhere in the design and think it's going to work. It's got to be done smartly. So the wafer guys are not off the hook on this either. Because if you go through different people's processes, which I've had the unfortunate pleasure of doing, there are still some on-wafer challenges for EM as well. Very similar things with the metals. In-fab resistance are normally 4-point on a very large structure. Okay, I'm good. There's no shape or CD information included in that. Thickness, like a profilometer, includes every metal in the stack, which is typically how they'll measure the stuff. And they're not usually a single stack. And I'll give a more detailed example of that one. Optical in-fab measurements use a reflectometer and ellipsometer to measure especially for MIM capacitors. They do an optical measurement and look at the fringes that come back to figure out how thick it is. This has got some problems, but there's ways around it. And I'll show that in a second. So optness from the mid, but they don't get epsilon from that. The surface morphology can matter, like what are you measuring it on? You're measuring on a metal, on silicon, on gas wafer, they're all different. And the other thing is, as we go to higher frequency, I would say almost nobody's PDK includes all of the dielectric layers that are on the wafer in the EM stack. They usually take some estimate and just say, oh, they only need from here. And it's not really true. At higher frequencies, you need all of it, and in variation over topology. So the metal stuff, here if you plate the metal, you get really great looking rectangles. If you evaporate it, it's more like trapezoids. And if you sputter it, it's just a blob. And so you can't really monitor this very easily by just using a traditional resistive line measurement, because what that gives you is the cross-sectional area, right? So the cross-sectional area is great for the resistance, but it doesn't tell me about the capacitance, right? So the capacitance is dominated by this layer, the facing layer. And so that's usually not captured in this stuff. So the metal stack stuff, this is just, it's simple math, right? Just showing I'm adding up 3 metals in parallel. The impact of that is we're measuring it down here at DC. So fab guy is, those conductivity numbers, fab guy is saying are here, but once you go up to high frequency, depending on how you made the metals, you can get a 50% increase. And that's not accounted for anywhere in the simulation. So that's kind of a problem. The roughness thing, if you deposit a dielectric on and you wind up having it rough because it's on a rough substrate, you're going to measure an average thickness from all of these little spikes, which is great. You get a number. Like they get a number back out of the reflectometer. But what you have to do because of that is you have to couple that with measurements of on-wafer PCM and use that to extract the dielectric constant. So that you're going to get an effective dielectric constant. The real physical one may be one thing, but the one that will get the EM simulation right is the effective one. So you have to tune for that. And this roughness isn't as bad as the laminate metal roughness. This is not enough to cause you issues where you got to include it too much at sort of lower frequencies. It's not the same order of magnitude. One of these numbers here. It's a lot smaller. It's on the order of like a few angstroms. It's not microns or thousands of microns. So it doesn't have any real impact on the end, but it has a huge impact on the breakdown when you've got roughness. Because if you get those spikes, it'll break down at that point. This is just showing, so we're in San Antonio. This is the Rough Riders. This is like Teddy Roosevelt recruited them here at the bar over there. So we're going to throw that in for historical value. And this just shows you like the roughness isn't as bad as the other metals, but it's still something you have to consider because it's affecting the thickness that the fab guys think it is, right? And so here's an example of capacitance over area versus 1 over the thickness, where this 1 over thickness is coming from what the fab guy is saying. If you plot that line, you can get a dielectric constant that works for EM simulation for gamma IM fabs. So, laminate simulation is really important. Module users or designers need physical and electrical information about what's going on, and a validation methodology would be great. PCM like Dropman would be fantastic if it's even possible to get something that will work that well. Challenges, statistics is like critical for this because of those thickness variations that I showed before. The metal profiles, you have to know really what's on the wafer ultimately is what these two guys are saying. And really we want those dielectric constants and loss tangents over broadband stuff, not just single points. And on wafer, there's still a few challenges, and then the through wafer vias and bumps and things like that are still issues. That's it. Thank you.
Looks like we got time for maybe 1 or 2 questions, real quick. I don't think we have a microphone for the audience, so if you can speak as loudly as possible with your question. Anyone? Okay, I kind of have a quick question for you. It seems like as many things as you said could go wrong there. It seems like I'm curious how you ever get something that matches what you model.
Well, I think at low frequency, some of the stuff isn't as bad, but Where it winds up hitting us is on yield, or somebody will build a part, they'll get something at one end of the distribution, oh, send it to the guy and let him sample it. It looks great, and then you give him the next one, it looks lousy.
Okay.
So it's more of a yield question for a lot of it. But for the higher frequency stuff, the questions were coming back because it didn't even look like the stacks that we're getting looked realistic. And so that's the designer will look at it and say like, oh, this looks wrong. It's like, well, then that's part of it is like, okay, well, here's all the reasons why that might look wrong. But your
Okay.
stuff, you can maybe include something that works.
All right. All right, well, let's thank our speaker again. Thank you.